Hello everyone, in this module we're going to look at a hypothesis test for two means, which basically means we're going to look at two populations. We're going to look at mu1 versus mu2. What we have been doing so far is only one population. But the case when the standard deviation is unknown, as well as we'll also talk about when the standard deviation is known. And with that we mean population standard deviation. So specifically, we're going to look at two-sample t-test versus paired t-test. Paired t-test will be the second part of this module. We're going to look at the two-sample t-test first, which are tests for two population means when standard deviation is unknown. And when it's known, it's called two-sample z-test. So we'll look at the difference between unknown and known standard deviations. And we will conduct those hypothesis tests using critical regions, p-values, and confidence intervals as before. And in the second part, we'll look at paired t-test. So far, we have been always looking at hypothesis tests and confidence intervals on a single parameter. Basically, where we have a single population and we look at the mean of that population or proportion of that population. And we test a mu or a p versus different numbers that we hypothesize. But now we're going to extend that to two populations today. And the application of that is when you want to study the difference between parameters, in this case means, mu1 and mu2. We want to study the difference between mu1 and mu2, mu1 minus mu2. And some examples of that in real life is, let's say, drying time of two different formulations of a paint primer, or lifespan of two different brands of tires, or processing time of two different machines. In all these examples, what you see is we have two populations, two brands of tire, two brands of paints, and two different machines. Let's look at comparing two means, mu1 and mu2, and it matters whether the data is paired or not paired. Those two populations, are they collected in a paired fashion or not paired fashion? So paired data is when you collect the data from the same subjects. Let's say here is cancer patient tumor size before and after treatment. So here you notice that the patients are the same patients that you collected data from. So that fact makes it a paired data. These are the same patients that you collected your samples from. So that means the data is paired. But unpaired data is when the subjects that you collected data from are two different populations, essentially. Female patient tumor size before treatment versus male cancer patient tumor size before treatment. So in this case, these patients and these patients are two different groups of people. And that makes it unpaired. So that's an unpaired data. And also, in addition to paired versus unpaired, it matters whether standard deviation of the population is known, and also what sample size are we using. And that will determine whether we're going to use a two-sample z-test versus two-sample t-test. And this is going to be the focus of the first part of this module, two-sample z-test versus two-sample t-test, when the data is unpaired. We're going to look at the paired data in the last part of this module. So, hypothesis test for two samples when data is not paired. And in those cases, we're essentially testing the difference between mu1 and mu2. And this is how we set up our null and alternative hypothesis. We're looking at mu1 minus mu2, whether it's equal to delta naught or not equal to delta naught. And this delta naught is some value that you pick. But delta naught is commonly, the most common value for delta naught is 0. which means we're going to look at if there is any difference between mu1 and mu2. By picking 0 for delta naught, that implies that we're going to look at any difference, if there's any difference that exists between mu1 and mu2. So that this type of test can be two-sided, as you can see here, or it can be one-sided, just like the other hypothesis test that you have seen before. So the way that we conduct our hypotheses is by using sample averages, x bar 1 and x bar 2, as an estimate for mu1 minus mu2. So these are sample averages. And the two assumptions that we have here is the two populations are independent and also normally distributed. So much like the test that we had on a single population before, it matters whether standard deviation is known or not. And by standard deviation, we mean the population standard deviation, sigma, whether it's known or not. And that determines whether we're going to use a z-test or a t-test. So this part of the slide is very important. We're going to use the z-score and a two-sample z-test if both standard deviations from both populations are known, or, and I want to emphasize here, this is an or statement. So either of these two conditions can lead us to a two-sample z-test, or number of samples of each population is greater than 30. But if not, we're going to use a two-sample t-test if both standard deviations are unknown, which means sigma 1 and sigma 2, and here is an and statement. So both of those conditions should be true. Sample size less than 30. In that case, we're going to use a two-sample t-test. So let's look at two-sample z-test first, which is the first scenario here. For a two-sample z-test, the test statistic that you calculate is this formula, and you'll see it's a function of sigmas and sample sizes and sample averages, as well as the delta naught choice that you have. And then once you calculate the test stat, you compare it with the critical region. Whether you're using a two-sided test or one-sided test, you have different critical regions. You're familiar with that. And that's a two-sample z-test. But that is for when the standard deviations are known. But if the standard deviation is unknown, but n or sample sizes are greater than 30, what do? Because we still need to use the z-test in that case. The standard deviations are unknown, but the sample size is greater than 30. Because this is an or condition, we got to use the z-test again. In those cases, we replace these sigmas or population standard deviations with sample standard deviations, with S1 and S2. And these are sample standard deviation. And that is if sigma 1 and sigma 2 are unknown, we replace them with sample standard deviations. How do we calculate sample standard deviations? When you collect the sample, you can calculate them using different statistical softwares, or if you're doing it by hand, S is equal to square root of summation of xi, and this summation is over I, minus x bar squared over n minus 1. And this means you take the difference of your sample data points with the average of the sample, you score them, you sum them up, you divide them by n minus 1, which is the sample size, minus 1, take the square root, that's your sample standard deviation. And that was a two-sample z-test using critical region and the test stat that you have. But if you're doing a two-sample t-test for when the standard deviations are unknown and sample size is less than 30, this is how you calculate your test-stat. As you can see here, you have sample standard deviations, and this will be your t-score, meaning that you would have to compare them with the critical regions and the t-distribution. If your test is a two-sided test, the critical region is greater than t of alpha over 2, and this is a new parameter that you see. It's called nu. It's a Greek letter nu, and that indicates the degree of freedom, right? Degree of freedom. If you remember, you have a degree of freedom on a t distribution, and that used to be n-1 for a one sample test, but now here is nu. What is nu? How do we determine nu? Because you see it in one sample or one-sided tests as well. The way we calculate the degree of freedom is here. Degree of freedom is a function of sample standard deviations, S1 and S2, and n values, sample sizes. So once you calculate that, this here is the round down operator. So you have to round down your number if it has decimal places, and you'll get the degree of freedom. So if your number ends up being 34.8, let's say, you always round that down to 34. Okay? And that's your degree of freedom. And once you have the degree of freedom, you can read this value from the t-table. Because you have the alpha of your test, you have the degree of freedom, you read that and you compare it with the t-score. The way we calculate the p-value, these are p-value formulas for two-sided tests and one-sided tests, is, again, you need the nu, or degree of freedom, as you can see here. And we'll show, we'll look at the application of these formulas in one example in a second. So it's basically 2 times probability of t of nu greater than absolute value of t-score. This t-score is the test-stat that you had here. For the confidence interval, for a two-sided confidence interval, as you can see, this confidence interval is constructed on mu1 minus mu2. Is the confidence interval of the difference between population means. And this is the lower confidence limit, and this is the upper confidence limit. As you can see, everything is everything look familiar here. Is X bar values for sample averages. This is the t-score. Oh, sorry, this is the t-value that you read, and sample standard deviations and sample sizes. And also we have the upper confidence limit here for one-sided tests. This is upper confidence limit when the type of test that you're doing is one-sided, of mu1 minus mu2 less than sigma, when your alternative hypothesis is that. You have an upper confidence limit, and lower confidence limit is just unbounded, negative infinity. And for a lower confidence limit, which is here, is used when you have a hypothesis test of mu1 minus mu2 greater than 0. So you calculate the confidence intervals that way. What we're going to do in the next video is we're going to look at one example to make these more clear.